partial tidal disruptions of white dwarfs and IMDHs.
Well, thanks for having me talk, and I'm happy to share some new results with you of relativistic simulations between white dwarfs and intermediate mass black holes in collaboration with Timur Bogdanovich and Cheng. Here's just some introductory snapshots of the star as it partially disrupts. These are plots of Mach numbers, so to give you an idea, the lobes streaming off the star are flying off at supersonically and up to Mach 5, where these dark regions indicate Mach 1 or subsonic flow, and then the outflow up to white goes to Mach 5 or greater. Okay, so it's nice to follow Mike because he gave a good introduction, but then I just want to have an introductory slide showing the parameters involved in studying tidal disruption. So this will be different. Instead of talking about comparative accelerations between the self-gravity and the tidal acceleration, actually I like to consider the disruption event to be a comparison of two timescales, one being the orbital timescale at periastron, and the other being the stellar dynamical timescale. And when these two are comparable, the star disrupts. So at A is equal to 1, we have the tidal radius being at periastron. So just to go back again, so if you choose a parameter and you choose the mass of the star and the radius of the star, you can have a periastron from that. So when eta is greater than 1, the star partially disrupts. And so when eta is between 1 and 3, there's partial mass loss from the star, but it doesn't fully disrupt. But for eta greater than 3, the star just gets tidally perturbed. So another parameter that is of interest is the mass ratio, and here I define it as n star over the mass of the black hole. So here's my slide where I describe my marker. Describe the numerical method. We calculate this disruption in a local moving frame centered on the star. And I think I'll draw a little diagram on the bottom just to give you an idea. Let's call this
Lights?
sure. Let's call this our black hole. Let's give you a black hole right here. So this large blob will be our star. So in the black hole frame, we have coordinates, and here we use Schwarzschild coordinates. Schwarzschild black hole, we have black hole coordinates, and we have the black hole port velocities. But for our system, we consider a coordinate system centered on the star, and so we have this in terms of the Fermi normal coordinates, which Mike was describing, which I think didn't say Fermi normal coordinates, but that's fine. So as we use proper time, and then x, y, and z, and likewise we can have velocities. And so we know what the origin of this, we know what the location of the position of the coordinate system, identified by this. And so we choose a trajectory, and we choose a geodesic, and for our purposes, we consider parabolic orbit. This is the relativistic specific orbital energy, and then some specific angular momentum. And so we choose a geodesic like above, and construct the Fermi normal coordinates, and then parallel transport this along the orbit, which I mentioned. And in doing so, we were able to construct a tidal potential that Mike mentioned, where you can have a quadrupole and then a higher moments. But since we consider Newtonian stars, we can actually also use Newtonian self-gravity and hydro to describe the star. And so we also have the self-gravity potential. And I should write this in terms of coordinates in the Fermi normal frame. Okay. So here are the encounters that we consider. So encounters between a 500 solar mass black hole and a 10 to the 4 solar mass black hole. The star that we choose is a white dwarf, an n equals 1.5 polytrope gamma 5/3 model, with m star being 0.64 solar masses and the radius being around 10 to 9 centimeters. And so we consider encounters up to the threshold of disruptance. So here you'll see in the black lines the 8 is equal to 1 encounter, where, actually it goes this way, where these are trajectories of the FNC frame. We'll say that the gray circle represents the tidal radius, so periastron is at the tidal radius. For 8 is equal to or partially disruptive encounter, the periastron is much further than the tidal radius. So for an encounter with a 500 solar mass black hole, the tidal radius is at 107 m, while at a 10 to the 4 solar mass black hole, the tidal radius is at roughly 10 m. So the time scale that we use is for the local moving frame, and so we take our fundamental time scale to be the fundamental radial pulsation period of an n equals 1.5 polytrope, so that's 10 seconds. So we model the encounter for 10 seconds in the star's frame, 5 seconds in the star's frame up to periastron, and then 10 seconds as it passes. Later we can talk about putting them in terms of actual orbital timescales, but we'll do that maybe on Friday or something, or maybe after this talk. Okay, all right, so here are plots, density contour plots in the FNC domain, and this is, I guess, also in the orbital plane of the star, or of the black hole. And so we have a partially disruptive encounter with a 500 solar mass black hole. I should mention that for this encounter, for these encounters, the radius of the star is about 11 m, so the extent of the domain is about 100 m. And mind you, the periastron is much further than 107 m for these encounters. It's like possibly up to 200 m. So in the FNC, in the black hole frame, the star orbits around the black hole. But in the FNC frame, the black hole orbits around the star, and so the black arrows indicate the direction between the black hole and the origin of the FNC frame. And so these are snapshots after periastron. 1, 2, 3 dynamical timescales of the star. So we'll see as this occurs, the tidal lobes are streaming off of the star, one being directed towards the black hole. But you also see that the core actually rotates a little faster than these tidal lobes, and so it will run in or come crashing into the lobes. Let's see here. The next plot, I show an energy plot of the same encounter for the binding energy and the orbital energy. I should say this is a receipt. All right. Anyway, sorry about that. So let's consider a little debris element. In the FNC domain, we have X, we have X, Y, Z, and UA. But we can transform this into the black hole frame in order to get the orbital, specific orbital energy and the angular momentum of the star, the debris element. So that's how we consider what is bound or unbound to the black hole. To consider what is bound or unbound in the star, we take the tidal potential and the stellar and the self-gravity potential and consider through an energy consideration what is bound and what is unbound. So considering the dynamical stability in an energy way, we describe this as the debris element has some internal energy, the debris element has some kinetic energy in terms of thermal velocities. It has energy due to self-gravity and the energy due to the external tidal potential. Okay, so that's what I plotted here. So I just wanted to have an equation to show you guys. So in the blue is material that is unbound from the star. So when E is greater than 0, K is greater than 0, then it's unbound from the star. So we have here at the edges of the tidal lobes. material that is bound to the black hole is outlined in red in the shaded region, so we see that the tidal lobe that is directed towards the black hole is actually bound to the black hole, and that makes sense. So we also see that as the core rotates into the tidal loops, material becomes unbound from the star. Okay, so let's talk about mass loss. So for all of the results I show you today are encounters between these two black holes. So here we consider how much mass is lost from the star, that is unbound from the star. And so on this axis we have the normalized change in mass, and then we have it as a function of time. This is zeros at period center. We have this for a 500 solar mass black hole and a 10 to the 4 solar mass black hole. And we have nominally the same encounter strengths that I defined by the second slide that I had. So then we compare the mass loss in between these two things. So we see that that there is a slight shift, and there's more mass loss for a more relativistic encounter. And I can point this out, I think. But if we look at two different orbits, this is at 107 m and this is at 10 m. The star spends a lot more time closer to the black hole here. It's at 10 m, and so there's relativistic tide in orbit that is affecting the star as compared to a more Newtonian encounter. So, if you take a look at, I want you to, I guess, remember 8 is equal to 2.5 because it will come up in the next slide or two. We see that for this encounter, we have about 0.01 while for this encounter with this black hole, but then in fact it's much larger for this encounter. I should also mention that, like I said before, we're tracking the amount of mass that leaves the domain. This mass leaves the domain supersonically, so it's not causally collected hydrodynamically to the star. However, when it leaves the domain, we are not accurately calculating the self-gravity of the star as well. So that is one caveat that I want you to remember. Okay, so tidal disruption is an asymmetrical process. We see that in many different tidal encounters. In previous studies, just identifying the asymmetric part of the tidal potential, we noted that for an asymmetric process, this is with only the quadrupole, and this is with the quadrupole and octupole. With the asymmetrical tide, we find that there's an asymmetrical star for this partial disruptive encounter. But we also see that when there is the asymmetrical tide, the star gets deflected off its initial trajectory. Okay, so here we calculate, so it gets kicked off its initial trajectory. Where does it get kicked to? Does it get more bound, or does it get kicked out of the system? And so here we investigate studies that have been done by Faber et al. And Manoukian et al. But this for our white dwarf intermediate mass black hole encounter, and we find a similar result. So here we consider the core to be material that is bound to the star by that equation. And so we consider what its the specific orbital energy is during the encounter. And so this is for the two different black hole masses and different encounter strengths. And we see that for partially disruptive encounter, well, for just a perturbed encounter, the star becomes more bound, and it's very difficult to see, but it transfers just very little orbital energy to the star. We see that as we progress and lose more mass, we have a star that is unbound. If we compare this to what this encounter with a 10 to the 4 mass ratio, we see that while only the eta is equal to, well, I went back. Well, here only eta is equal to 2 is unbound, but we also see that eta is equal to 2 and eta is equal to 2.5 is unbound. And for these encounters, there's a little bit more mass loss. We go ahead and calculate what since we have a positive orbital energy, we calculate what the velocity would be at infinity. And so we find for these encounters, we have about 843 kilometers per second for our fastest encounter, eta is equal to 2, and then we also have 1,500 kilometers the core goes, we also consider just in generally what the variation in the orbital parameters of the debris after the event. These are all results after 10 timescales after pre-astron passage. This includes material that has flowed out of the domain as well as remains in the star. All right, so again, left side is 500 solar masses and then 4 solar masses on the right. These are mass histograms. So we see that for encounters, this is, by the way, a 8 is equal to 1 threshold disruption encounter. We see that for an encounter with a 500 solar mass black hole, it has this around the same spread of energy as it does with 10 to the 4, but we see that there is a larger spread in the specific orbital length of momentum. I should mention, before we go into DMDE plots, all the material that is 0 here, less than 0, is bound to the black hole, and all the material that is greater than 0 is unbound to the black hole. So if we compare these plots, these 2D histograms, with what is usually used, the DM over DE, which we see in, actually we didn't see any of these. So this is a plot of DMDE after the simulation ended. This includes material that's flowed out of the domain that remains in the domain. Let's take a look at first these 1D plots. This is DMDE versus the variation in specific orbital energy. Here I also plot what is unbound to the star, what is bound to the star, and then also the total. We see that for an encounter with a 10 to the 4 solar mass black hole, it's more disruptive, so there's less material that is bound. Let's see here. So if we think about in terms of the light curve, this material represents, it has the most bound energy, so it's the early return, while the material still in domain represents the late time return debris, late time debris. Okay, so I plot. So take the orbital parameters of the debris. I also, from this, we can calculate its semi-major axis, new periasterons, apasterons, eccentricity. You can also calculate return period. And so here we make a mass histogram that, it's funny, Mike and I never talked about this, but well, I'm curious of a mass histogram for you. So this shows the return periods. This is for the first return. In years, we have m dot divided by m Eddington, and we see that it's for, and I actually, this is in terms of mu, the mass ratio, but the dotted line should be an encounter with a 500 solar mass black hole, and this line is an encounter with a 10 to the 4 solar mass black hole. We see that this is extremely super Eddington. This is what we get by taking a look at the orbital parameters debris and just making an estimate. But this is something that has been seen before, say in the Haas et al. Simulations for these types of encounters with a 100 or I think 1,000 solar mass black hole. But this is at almost 10 times the Eddington rate. The biggest question here is how does a accretion disk form? And it's discussed a little bit in Haas et al. But here I would bring this big elephant to you, all of you. So it's much lower for an encounter with a 10 to the 4 black hole. Yeah, but I should also mention, the accuracy of this estimate is good for the early times because I'm tracking debris that's leaving the domain very early. So all the material that is still in the domain represents this later t to negative 5/3 fall. As I said before, since material is streaming out of the domain, I can't accurately calculate the self-gravity of the debris. So this is all material that has to be studied with a better code that can describe it. Okay. So now So like I mentioned before, I can take a look at semi-major axis versus eccentricity. You know, with all the caveats, might as well just look at other parameters. So these are mass histograms as well. 500 solar mass black hole, 10⁴ solar mass black hole. We see that the eccentricities of the debris, well, you know, initially the orbit is at a parabolic, but we have debris that goes up to about 0.8. But for the more relativistic encounter, we have eccentricity that is only up to 0.94. If we take a look at you know, semi-major axis, we see that there's a wide range of eccentricity for at one semi-major axis, and it's very narrow for the relativistic case. So this brings up the issue. Perhaps there are more intersecting orbits for an encounter with a 500 solar. How much time do I have?
About 7 to 8 minutes.
Okay. Well, I'll open for questions then. Okay, so just to make a summary, we do relativistic encounters between white dwarfs and massive non-spinning black holes, threshold disruption. We calculate the kick of the rim core off the orbit. We estimate the orbital parameters of debris, treat them as ballistic. We just calculate the return period after the first return. Bring up the caveat that new calculations are needed to address self-gravity of the streams, and this has been done before by Cheng and Willishan et al. And so these results to show to highlight distinctions in encounters between a different mass ratio, where where I guess the 10⁴ solar mass black hole is at a very close to black hole at 10 tidal radius. Anyway, so future work includes tidal interaction due to the spinning black hole, and we also can apply the same procedure to main sequence star destruction. And I think I might as well show you a video because it's not too thematic, but might as well. So this is a Mach number for this partially disrupted event. You see that it goes up to 5 or greater actually for in Mach number. So material is very supersonic. And so to remind you, the gray area is for subsonic flow.
Which combination of parameters is that?
This is a so this is an encounter with a 500 solar mass black hole, and this is, I think, maybe an 80 to 2.5 or so encounter, which we're just have to think about in terms of data later.